to today's webinar, Regain Mobility in Malnourished Patients. On behalf of Nestlé Health Science, thank you for taking time out and being here today. My name is Nuria Barcons, and I am the Global Medical Affairs Lead for Adult Medical Care. We in Nestlé Health Science believe that nutrition can be life-transforming for those who need extra support during short and long-term medical challenges, and nutrition can positively impact people's quality of life. Today, we will be discussing how muscle mass is regulated and how muscle protein synthesis and muscle protein breakdown are stimulated with an optimal protein and omega-3 ingestion and loading. For talking about it, we have one of the top experts in the field. I'm honored to introduce to you Professor Stuart Phillips. Professor Phillips is a full professor in the Department of Kinesiology and a member of the School of Medicine at McMaster University in Ontario. He's Tier 1 Canada Research Chair in Skeletal Muscle Health. He's also the director of the McMaster University Physical Activity Center of Excellence. Author of more than 220 original research papers and 90 reviews, named on 2018, 2019, 2020, and recently 2021 in the international list of highly cited researches compiled by Clarivate Analytics. Thank you, Professor Phillips, for accepting our invitation. But before giving the floor to you, I would like to inform the participants that we will be running a live Q&A at the end of the webinar. Please type your questions into the chat window. Professor Phillips will address them during the Q&A. It's time for enjoying and learning the power of protein and exercise combination in mitigating inactivity and disuse. Enjoy.
It's a pleasure to be here with you today to talk to you about regaining mobility in malnourished patients, the power of protein and exercise combinations in mitigating inactivity and disuse. Before we get started, these are my funding and disclosures. The key concept that I want to talk to you about today is sarcopenia, or what we know as the age-related decline in muscle mass, strength, and function. Traditionally, we're told that muscle mass declines at a rate of about 1% per year and muscle strength at a rate of about 3% per year. The reasons for sarcopenia are multifactorial. They likely involve hormones, changes in vascular reactivity, processes that are inherent to the muscle itself, but there are two key processes that change over which we have control. The first of which is physical activity, and the second of which is nutrition. However, as people age, we know that they respond to a smaller degree to stimuli of physical activity and nutrition, which is a condition that we call anabolic resistance, and that we think is one of the main reasons why older people lose muscle mass as they age. A key paper that I'm going to refer to throughout this presentation to convince people that older people require more protein is the following. This was written by Dan Traylor when he was a postdoc in my lab. What we found in this paper is that there were key studies in which protein requirements for older adults have been assessed. Interestingly, however, the studies here shown in blue were the studies that put the protein intake for older adults at about 0.8 grams of protein per kilo per day, whereas the studies shown in green actually predicted that older adults would need more protein to be in nitrogen balance or in protein balance. I think the important point, however, is that it's this study conducted by Bill Rand, Peter Pellet, and Vernon Young that forms the basis for the recommended dietary allowance or the recommended nutrient intake, which hovers variously around 0.8 grams of protein per kilo per day. When we looked at the individual studies, we could find that the nitrogen balance study that Rand used, however, only had 14 individuals out of 235 total data points that were older. And so we thought maybe there wasn't enough data. However, the Campbell study did find that older individuals could probably be okay consuming protein at the RDA. However, Humayan et al. Reanalyzed the RAND data and showed that actually older individuals probably had a protein requirement much closer to 1.05. When you look at other studies that have used the method of the indicator amino acid oxidation, you can see that protein requirements for older individuals are much higher, about 1.2 grams per kilo per day. When you average all of these, you come out with an intake that an older person would need to balance protein losses and be safe of about 1.16 grams of protein per kilo per day. And those types of intakes are reflected in the recommendations from several working groups. Instead of the recommended dietary allowance here at 0.8, you can see that the minimum protein intake is likely between 1 to 1.2 or 25 to 50% higher. If you have an acute or chronic disease, it's higher still. And with severe illness, injury, or marked malnutrition or undernutrition, it could be as high as 2 grams of protein per kilo per day. So how much protein are older people consuming? The answer that you'll often hear is based on the RDA intake. In other words, when we looked at this using actual 3-day diet records, we could see that men and women over the age of 71 years, when we looked at the estimated average requirement in the recommended dietary allowance, that it's a trivial amount of individuals who are consuming below this intake, although there are some. However, when we consider that the intake is probably insufficient and we use the proposed estimated average requirement and the RDA of about 1.2, you begin to see that it's almost 90% of older individuals over the age of 71 years that are consuming an insufficient amount of dietary protein. And just to emphasize the point that dietary protein is important, I want to show you this clinical trial published by Dr. Young-Soon Park, in which she had 3 different protein intake levels from the RDA to 1.2 to 1.5 in pre-frail and frail older subjects that were malnourished. You can see that the change in appendicular skeletal muscle mass is a staircase effect, and that's true whether we normalize this for weight. Interestingly enough, you can see that gait speed increased in all 3 groups. However, it was a staircase effect in which the effect was greatest in that for the highest protein intake group. But I think it's important to appreciate a number of other protein-related points. First of all, consumption of greater proportions of dietary energy from protein is associated with a lower risk of protein energy malnutrition. At the same time, consumption of greater proportions of dietary energy from protein is associated with greater healthy eating index scores, mostly due to increased consumption of nutrients of concern from animal source proteins in older people. And finally, consumption of a greater proportion of protein and a higher diet quality is associated with a greater hand grip strength and a lower incidence of functional limitations. All of these are published randomized controlled trials, and it emphasizes some really important points that I think are worth discussing. First of all, aging is associated with a reduced food intake, which is a predisposition for energy or protein undernutrition, and in some cases, overt malnutrition, particularly in frail and institutionalized older people. We know that muscle area and strength are reduced in older people that are fed a weight-maintaining diet that contains protein at the RDA. So we're losing muscle mass on an intake that is recommended for almost 98% of individuals. So older adults need more protein than the RDA. At a minimum, it's between 1 to 1.2 grams to maintain muscle mass, and we could see greater benefit with even higher intakes. And importantly, older adults are not consuming these intakes. So there's key concepts that we need to understand before delving a little bit further into this issue. One of them is to understand muscle protein turnover. Muscle protein turnover can be envisioned as a brick wall. There are bricks going into the wall. They're provided by amino acids, and that's the process of muscle protein synthesis. But simultaneously, there are bricks being taken out of the wall, and that's muscle protein breakdown. We know that these two processes go on dynamically and they oppose each other, but they fluctuate on a meal-to-meal basis. And that's shown schematically in this figure. You can see with each ingestion of protein here at the breakfast lunchtime, and dinner time meals, we get a robust stimulation of protein synthesis that subsequently declines and then is stimulated again, and finally is stimulated for the final time at the last meal of the day. Protein breakdown doesn't change too much, but you can see that the net area of green, which would represent muscle protein accretion, is relatively small and short-lived, and it's balanced against an area of loss, shown in the gray here. In other words, you would lose just about the same amount of muscle that you would gain, proportional to the number of meals that you would eat containing sufficient protein. There would obviously be a large gray bubble at the end of the day here that I haven't shown, which is when somebody is sleeping, so they're not consuming any more protein. When we have someone exercise, and the exercise that I'm talking about in this situation specifically is resistive exercise, so loading exercise that in younger individuals would result in muscle hypertrophy, but what we're trying to do in older individuals is actually to mitigate muscle loss. With exercise, the amplitude of protein synthesis is greater. Quite simply, we see a greater fed state gain in muscle. At the same time, the decline in the fasted state is smaller. It doesn't take much to see that over time, this would result in an increase in muscle protein concentration and an increase in muscle size, or at least a mitigation of muscle loss. However, with aging, the phenomenon of anabolic resistance results in the opposite adaptation. So we don't get the same robust stimulation of muscle protein synthesis. Instead, we get a muted response. And you can see that now the net areas of muscle gain are going to be smaller than the net areas of muscle loss. So what causes anabolic resistance in aging? I need to thank Dr. James McKendry for this fantastic figure, which shows that it's probably multifactorial. We could have things like reduced intake of protein or reduced intake of high quality proteins, a reduction in physical activity, impairments in anabolic signaling, microvascular impairments, inflammation, greater splanchnic sequestration, reduced amino acid uptake, or impaired digestion and absorption. What the result is the per meal protein dose in older individuals required to optimally stimulate muscle protein synthesis is lower. That's shown in this figure, which is a study conducted by Dan Moore, which was a retrospective analysis of data from our lab and that of Kevin Tipton and Oliver Wittard. We've got young individuals in the left-hand graph, older individuals in the right-hand graph, men in both cases, average age of about 22, an average age of about 70. You can see that muscle protein synthesis, or myofibrillar in this case, so the force-generating proteins, rises to a point, and then the line inflects and doesn't go any higher at an intake of about 1/4 gram of protein. Adding a confidence interval, we could go as high as 0.3 grams per kilo per meal. Move over to the right, and you can see that that intake is shifted to the right, and the break point occurs at 0.39 grams of protein per kilo, or almost 0.57 grams of protein per kilo, adding a 90% confidence interval, which is about 1.7 times greater than it is in younger individuals. So what does that look like in reality? Thank you to Sarah Oikawa, former PhD student of mine, for drawing this fantastic figure to illustrate that muscle protein synthesis is stimulated in direct proportion to the amount of protein. In other words, it's a dose response. And most people consume a small amount of protein at breakfast, a moderate amount of protein at their lunchtime meal, and their largest amount of protein at their dinner time meal. Sarah is included in this figure, pre-bedtime snack, and then the overnight fasted loss. You can see that the rises in muscle protein synthesis are proportional to per meal intakes, but just remember that those are much higher in older people than they are in younger people. So if we look at an 85 kilogram younger person, they're hitting that per meal intake on 2 occasions here, at lunch and dinner. In fact, they're exceeding it at dinner time by a large margin. Older people, on the other hand, the same 85 kilogram individual who might be 70 years old would need at least 0.4 grams of protein per kilogram per meal, which brings into question whether the protein source is important. So a good question is, do we know what the active amino acid, or is it all of the amino acids, in particular the essential amino acids, are needed? It is in fact the single amino acid leucine, which is a branch chain amino acid that triggers an anabolic pathway signaling through a canonical protein known as mTOR. And we now know through work in David Sabatini's lab at MIT that this process signals through something called cestrin-2, and it triggers a translocation of the mTOR complex to be able to use amino acids more efficiently. I want to show you some work that comes from our group, and this is Tyler Churchwood-Vinay, who was a PhD student at the time, and he's got two important conditions in this experiment. They are 6 grams of whey and 25 grams of whey. So this would be a small dose and almost 4 times as large here in younger individuals. And then he's got a small dose of protein to which he's added back a large amount of leucine. You can see that there's initially a stimulation of protein synthesis in all 3 of these conditions. However, it only continues in the large dose of whey or in the small dose of whey to which we've added back leucine. So quite simply, we can make a really small dose of whey protein look much bigger by adding back crystalline leucine itself, indicating that it's leucine that's the important amino acid in stimulating muscle protein synthesis. And so long as you have sufficient essential amino acids to support that anabolic response, you get a full and robust response. Now, this is an acute infusion over about 4 to 5 hours. But we've recently been able to, using technological advances in mass spectrometry, use ingested deuterated water to measure protein synthesis over days. And that allows us to be able to look more fully at the response that is a result of adaptations in dietary levels, adaptations in physical activity levels, including sleep and all other processes of daily living. When we do this, as opposed to the infusion, we don't have to have the subject in the lab. We can let them go out and do their regular activities. And the ingested deuterated water response is a much safer proposition than infusing the tracers. To show you what we found, this is work highlighted by Keelan Murphy, who was a PhD student in my lab at the time, in which she had older men, average age of about 70 years, consume a lower protein intake, or the RDA, or a higher protein intake, or about 1.2 grams per kilo per day. And then we added 5 grams of crystalline leucine to every one of their meals by a beverage, or we gave them a placebo drink. What you can see immediately in the rested condition is that the addition of leucine at the lower or the higher protein intake additively stimulated fractional synthetic rate of proteins over about 5 days. So this is a per day rate of protein synthesis. When we add resistance exercise, however, we always get a greater anabolic response, which is indicated here, either whether it's the placebo group, but we get a greater anabolic response in the leucine ingested group. Interestingly enough, the same phenomenon happens in older women. This is a study performed by Michaela DeVries, a postdoc in my lab at the time, who showed that in 2 groups of women, a control group and a group consuming leucine, it's consuming the exact same amount of protein clamped at 1 gram per kilo per day, average age of about 70 years, was greater in the leucine-enriched group. So there was a group consuming 2 leucine-enriched beverages per day, and you can see a greater rate of protein synthesis over about 5 days in the leucine group. Exercise always stimulates a greater anabolic response, whether you're control or leucine, but you can see it's greater in the leucine supplemented group. So it works in young men, it works in young women, and we get the similar responses in older men and older women over a period of about 4 to 5 days. That's led us, and it's not just our work, to propose what we call the leucine trigger hypothesis, and it goes something like this. Intracellular leucine concentrations in the muscle have to reach a certain threshold or trigger concentration to fully saturate the protein that I showed you earlier called cestrin-2. When that happens, we get a full and robust anabolic response. So you can see that a low dose of protein here doesn't quite reach the leucine trigger threshold, but we would get a small response. So it's perhaps not an on-off switch. It's sort of like a dimmer switch. In other words, you get some light or some response at a low dose, and you get a more robust response at a higher dose. However, the trigger itself is mobile, and the mobility is induced by physical activity. So the more active you are, and particularly resistance exercise, the trigger comes down transiently only, and so you have to keep repeating the phenomenon of exercise. So when the trigger comes down, we can get away with lower protein doses or lower doses of leucine. However, in the opposite direction, with aging, which is probably accompanied by reduced levels of physical activity, probably a reduced protein intake, mild insulin resistance, and definitely if you're in a state of inactivity like bed rest, the trigger moves to a higher level. And now we require either more leucine or more protein to trigger the full anabolic response. And I just want to show you a recent finding that has important ramifications, and it's from Glenda Courtney Martin's lab, and Sylvia Zwiga is the first author. What they did was using the indicator amino acid oxidation method. The conclusion was that the leucine requirement of these older adults is more than double the amount of the current recommendations. And they suggested that leucine could be a limiting amino acid in the diet of older adults consuming the protein RDA, or for those consuming a plant-based diet. And the importance of this is shown in the following study by Mathai et al. In this study, they looked at the dietary indispensable amino acid score, which is the most up-to-date scoring method for looking at protein quality as compared to, say, PD-Cas, for example, which I think most people would be familiar with. And you can quite quickly see that whey proteins, whether it's an isolated concentrate, a milk protein concentrate, or skim milk powder, have the highest scores. So the cap is removed in DIAS compared to PD-Cas, indicating that there are functional roles for certain essential amino acids. What the figure shows you here is that quite quickly is that the milk proteins are superior to plant proteins. This is pea protein concentrate, soy protein isolate, and soy protein, and wheat protein with respect to all of the essential amino acids and their ileal digestibility. Now we can look at this another way, and that would be using the leucine amino acid reference ratio, which is essentially a way of calibrating these proteins relative to their leucine content. And you get the same story. Whey protein isolate and milk protein concentrates have very high leucine content. And in fact, compared to two different soy protein isolates, pea protein, rice protein, and compared especially to collagen, which is very low in leucine, you can see that you'd have to eat twice as much of these proteins to get to the level of leucine intake that is provided here with the milk proteins, or 4 times as much collagen protein. But importantly, it can't just be the branch chain amino acids or leucine in and of itself. You have to have all of the essential amino acids. And that's highlighted in this paper by Cass Fuchs, who was a PhD student at the time working in Luc Van Loon's lab. In this study, they used servings of about 6 grams of branch chain or branch chain keto acids, which are effective without the nitrogen, but they still stimulate protein synthesis, versus milk protein, which would obviously be a blend of about 20% whey protein and 80% casein protein. So the sort of what we know as the traditional fast and slow protein blend. And when we look at that, you can see that there's an initial stimulation in all of these conditions. However, the continued stimulation of protein synthesis only happens in the milk protein. And that's probably because of the slow digesting rate of casein that's present in milk. So what does all of this mean in a scenario that happens with increasing frequency in older people? And I think is a watershed moment, and that's inactivity and disuse, in particular hospitalization or some procedure that results in people being off of their feet for a prolonged period of time. And I really need to acknowledge the contribution made here by Doug Patton-Jones, who recently passed away. And in this paper that he and Kirk English wrote, describing what is known as the catabolic crisis. And the catabolic crisis is a period essentially of disuse. And as the diagram here indicates, this is a theoretical cross-sectional scan of an older person's thigh. This is normal sarcopenic loss between 50 and 90. And this is what would the scan would look like in somebody who had experienced a severe catabolic or disuse event. It could be a surgery, it could be a flu, it could be even something like the global pandemic that we're all experiencing now. But you can see in this period of time that muscle loss is greatly accelerated and that these older people are now on a different downward trajectory. And it is exceptionally difficult to recover from these periods. Older people need to work exceptionally hard in rehabilitation to in any way try and reclaim some of their lost mass and definitely some of their lost function. So this leads to what we talk about as a cycle of inactivity-related sarcopenia. In other words, a period of muscle disuse because of a surgery, a flu, but definitely a hospitalization induces bed rest, inactivity. We know that older individuals in hospital eat less. We get the phenomenon of anabolic resistance. We get a loss of muscle, and that impairs recovery, and this becomes a vicious cycle. And I had the opportunity to write the paper with Doug and Don Lehman talking about optimizing adult protein intake during catabolic health conditions. And in this, we emphasize the need for early intervention with physical therapy in these patients, and the consumption of protein in close temporal proximity to physical therapy. In fact, we've learned a lot from athletes in this regard, but when younger athletes exercise, they get a robust anabolic response that older people do not. So we may need to emphasize high quality protein with high leucine and even other ingredients to enhance the efficacy of protein to mitigate the decline and help these patients recover. So it's not enough to just survive the catabolic event, but we need to thrive on the other side. So what other ingredients would be important? I think one of the primary ones would be omega-3 fatty acids. And just to show you a few of the papers out there that I think are good evidence bases for suggesting this. And quite simply, when we look at the supplementation with high doses of omega-3 fatty acids, we can see that in older people, there may not be an enhancement of fat and bone-free or lean mass, but there is an enhancement, and this meta-analysis shows it here, of grip strength. So that's an important functional outcome in older people that I think is something to take note of that happens with omega-3 polyunsaturated fatty acid supplementation. We're not exactly sure how omega-3 fatty acids work, but there are two working theories. The first of which is that we change the membrane fluidity by incorporating polyunsaturated fatty acids. And we do the same at the membrane of the mitochondria that enhances mitochondrial function. We know that this could enhance intracellular signaling and preventing anabolic resistance for a short period of time, or the decline in age-related mitochondrial function on top of inactivity-induced anabolic function. So what other supplements could we be talking about? One, of course, is vitamin D. In this short abbreviated list, I've tried to highlight in blue the papers that show good evidence for supplementation with vitamin D and probably calcium in preventing fractures. At the same time, the studies highlighted in green show muscle-specific outcomes like improvements in mobility and strength. But what if we put all of this together? What if we were to create a multi-ingredient supplement that had all of these ingredients and more that could address multiple deficiencies in older people? Just want to talk a little bit about multi-ingredient supplements and why multi-ingredient supplements might be more effective in helping older people mitigate age-related declines in muscle mass, muscle function, and particularly in those situations of disuse or anabolic crisis. So why might these supplements work? The schematic here shows a population of individuals in whom we're going to intervene with a particular supplement or an exercise intervention with the hope that it's going to show benefit in all of these individuals. So this would be like laying a blanket on top of everybody and expecting that the response variability that we would get from these individuals would be relatively low. In other words, we would always get a positive response. When we look at this in a waterfall style plot, it looks something like this. We'd expect that there would be some variability, that there would be people that had a lower response, but the net or aggregate effect is that everybody responds to the intervention. However, frequently we don't see that. What we often see is something like this. There are some people that don't respond at all, or may even respond in a negative fashion. There are some people in the middle that have a response that would be considered unremarkable. And there may be some people in the upper end of the scale that would have a greater response. Multi-ingredient supplements, however, work because they target multiple pathways. I'm going to show you what that means with respect to the population here. The first ingredient, and this could be something like protein, would enhance the anabolic effect of our intervention in these individuals because they had a lower protein intake coming into this. They were particularly frail, or they had a poor quality protein intake, and we've improved the intake of the key amino acid that we've talked about all along, which is leucine. The second ingredient could be something like omega-3 fatty acids. And the individuals highlighted here in yellow are particularly susceptible to the effects of changes in membrane fluidity. And so we get a greater anabolic response out of these individuals. The third ingredient might be something like vitamin D. What we've done in the individuals indicated in orange here is corrected either an overt deficiency or an insufficiency and restored their circulating 25-hydroxy-D levels back to normal. When we combine all three of these, we get a greater synergistic effect than each of the individual supplements together. So now we can begin to see that we get more individuals who are responding to our multi-ingredient supplement than if we gave each of those three ingredients separately. When we throw on that the intervention, which I think is probably most potent, and we can agree is probably going to get an effect out of most individuals, this is exercise. And in this situation, you can quickly see that most individuals who are supplemented and engaging in exercise, save for maybe a few individuals here, are going to experience some sort of positive, anabolic, beneficial outcome as a result of our intervention. So here are some takeaway points. First, protein is an important ingredient to counter age-related sarcopenia. A key amino acid in this process is leucine. It stimulates muscle protein synthesis, which is the key process in gaining muscle and also in mitigating its loss. At the same time, high-quality proteins like milk protein are highly effective. And we need to consider the addition of other ingredients like omega-3 fatty acids or vitamin D that are probably synergistic with protein in their ability to be able to reduce muscle loss, improve strength, and counteract sarcopenia. So multi-ingredient supplements are effective. They correct multiple deficiencies, they enhance multiple functions because they address multiple pathways that could be either impaired or not operating at their greatest efficiency in older individuals. And then when added to exercise, the efficacy of multi-ingredient supplements is enhanced even further. I want to thank you very much for taking the time, and I hope I can join you and answer some questions. Thank you.